today. But yeah.
Thanks, Chris. Good morning, everybody.
Good morning.
Okay, you want to try that again? Good morning, everybody.
Good morning.
Awesome. So, some of you have met me before. My name's PJ. I am one of the speakers, but you have to wait all the way till tomorrow to hear me speak. Because we wanted to start things off right. We wanted to start things off with the voice of the new generation. The young folks, the millennials. Those who get discounted sometimes on the Twitters and the blogs and things. But this person is not like that. This person has been working in computer science for many years, surprisingly more years than you'd expect given his age and demeanor. He's happy, he's go-lucky, he has a killer karaoke voice, and he might do a thing called R-Spec occasionally. Please welcome to the stage, Mr. Sam Phippen.
Hi folks, how's it going? Let me just unlock my iPad here. All right, good morning.
Good morning.
How's everyone doing today? Who is less jet lagged than me? Yeah, everyone I expect. I wanted to kick this off by asking, who is here for their very first Ruby conference? Who has never been to a Ruby conference before? Show of hands. All right, everyone else in the room, let's have a huge round of applause for those people. Welcome to our community. It's great to have you here. I hope you really, really enjoy this conference. I have been coming to Ruby conferences for many years at this point. I love it. It's one of my absolute favorite things to do, and I really hope you enjoy it too. Would all of the organizers and sponsors please make themselves very visible just by waving? Folks, these are the people who make this conference happen. We would not be here today without them, and so can we also have a huge round of applause for that? It's amazing. They give you a microphone and you have the power to make people do things. All right, so to introduce myself, my name is Sam Phippen. I'm a member of the RSpec core team and a senior software engineer and technology lead at DigitalOcean. And I have no slides. I'm just going to be talking. I have some notes on my iPad, so this should be a really nice, relaxing way to get into the conference. I've been thinking a lot recently about how computers fail, and more importantly, how the systems that we as engineers build fail when we're running them. I suspect most of you here work on some kind of software that has to be available 24/7 by 365, and that most of your engineers have some kind of core business hours. They have times when they are working, and they have times when they are not working. And the software has to keep going, even when those engineers aren't around. I suspect many of you have some concept of PagerDuty or on-call or the ability to be reached well out of hours. And this has recently become a very important idea to me because I've sort of transitioned from being someone who just writes software to someone who is leading a team of software engineers. And it's so important to me, I can't even begin to describe to you that they are happy and well-rested and they have time to hang out with their friends and their families and time away from the hell that is working on distributed systems. And so this talk really is my sort of musings on different kinds of failure and how I think we as engineers can improve. And I'd like to start with a personal story that begins at 10:24 Eastern Time on the 5th of April, 2017, when an engineer at DigitalOcean types a command into their terminal, hits enter, and our primary production database is dropped and falls off the face of the internet. Now, this is a really, really bad situation to be in. At the time, DigitalOcean is a significantly less distributed systems company than it is today. We manage everything: droplets, billing, customer support, logins, authentication, our forums, our community sites, out of this one ginormous database. And for it not to be available means that basically you can't do anything with our platform. We're gone. Now, fortunately, we did have a 3-hour delayed read replica, and we were able to restore from backups, but the point is, we were fully offline as a company for 5 hours in the middle of the business day in the US, and that's really bad for us. But more personally, I was the lead engineer for the team that the credential was used to drop that database for. And so, to some degree, this was a personal failing as well. While I wasn't the one who dropped the database, I was the one responsible for the credential that was used to do it. And I suspect many of you in this room are terrified of making mistakes like that, or have already made a mistake like that in your career. And if you have, you know that it sucks personally, but most likely you weren't fired for doing that, and most likely you went on and continued having a career and grew and got better as an engineer because of it. So that's my story. I'd like to move away a little bit from computers and talk about something completely different. It turns out that there are many other industries that have complex systems where people make mistakes and failures occur. And as I was reading and thinking about this subject, I encountered a paper published by the National Transportation Safety Board, or NTSB, in the US, literally entitled Runway, Overrun. And that's where the title for this talk comes from. I just stole it wholesale from the NTSB. Jackson Hole Airport in Wyoming is a notoriously difficult airport to land into. It is surrounded by mountains on 4 sides. And in the winter months, it gets icy and snowy. It has a relatively short runway. And pilots are given specific and special training on how to land in that airport. Which brings me to 11:37 a.m. on the 28th of December 2010, when American Airlines Flight 2253 lands on the runway at Jackson Hole, and then 36 seconds later goes off the end of the runway into a drift of snow. Now, fortunately, nobody in the aircraft was injured, everyone got out alive, and they were able to use the plane again. This, by the way, is what pilots call a great landing. If they weren't able to use the plane again, but everyone got out alive, that's what the pilots would have called a good landing. I'm serious, these are actual industry terms that they use. And so, what actually happened here? Well, as the plane came down to land, the pilots failed to deploy 2 critical mechanisms that are used to decelerate planes. One called speed brakes and one called thrust reversers. And that caused the braking force on the plane to be significantly less than was expected, and it went off the end of the runway. So let's stop for a second and just analyze a little bit about what I've said to you there. On the one hand, I've told you that an engineer dropped our production primary database, and on the other, I've told you that these 2 pilots failed to deploy critical mechanisms to stop the plane. What I'm doing here is blaming the people involved in the incidents and the complex failure that occurred. And the question then becomes, what can we learn from that analysis? Well, we could learn to hire better people, but I'd like to think that the engineers that I work with are pretty great, and I really want to believe that American Airlines pilots know how to fly planes. And so then the question becomes, well, they made mistakes. What if we just fired everyone who made a mistake? And that is a pretty ridiculous statement. I suspected if we applied that policy, nobody in the room would have a job. So this analysis isn't satisfactory. It doesn't get us to an answer about what happened that lets us fix the problem, make it go away, and do something to fix it going forward for all time. So let's go back to Jackson Hole and explore a little bit more about what happened. The captain of the plane, the pilot in charge, had over 20,000 hours of experience flying aircraft, with more than half of it in that specific plane that they were flying that day. The co-pilot, the secondary pilot in the plane, had more than 11,000 hours of flying time, with about a third of it on the specific plane that they were flying that day. These are not inexperienced people. These are people who know what they're doing. They have more total experience than I suspect most of the programmers in this room. And more importantly than that, pilots are trained to an extremely high degree, much higher than most software engineers ever are. And so it's unlikely that they would have made a simple mistake. We in fact have a really good model for understanding level of skill and expertise called the Dreyfus model of skill acquisition. In Dreyfus's model, you're ranked in skill level from one of 5 categories, starting at novice and going all the way through to expert. Novices have almost no skill and almost no ability to synthesize actions themselves. They must be given simple, easy to follow, repeatable processes in order to get anything done. The slightest deviation knocks them out of their comfort zone, and they really have no ability to get back into it without the help from an expert. These are your trainee nurses, or your sort of pilots at the very beginning of their training, or perhaps more importantly, programmers who are currently in boot camps. If any of you are in that situation, I'm going to go ahead and guess that you've recently been shown a process called TDD, the red-green refactor cycle of test-driven development. This matches the definition of novice in Dreyfus's model more or less exactly. It's a series of simple, repeatable steps that if you follow, you can go from 0 to functional software. But the moment you encounter something that isn't one of those 3 states, the moment you make a syntax error or have a dependency that fails to install or some complex file failing to load, that novice programmer is going to go back into that terrified state of being unable to deal with and work with the software system that they're working on. TDD is an incredible tool for teaching new programmers how to work, but it's not the be-all and end-all of software development. Experts in Dreyfus's scale have spent so much time and have developed so much experience in what they're doing that they process every input in parallel. They have intuition for nearly every situation. They understand on a deep and fundamental level what it is that they're doing, and at the same time, when they're performing actions, they can't explain to you why they're making the decisions they're making as quickly as they can. Watching a true expert in their field work is an amazing thing to see, and it never looks anything like what you as someone who's newer or less experienced can do. I will stand here on stage as a member of the RSpec core team and tell you I don't find TDD all that useful in my daily practice. Writing tests is a good idea, but the sequence of actions that I take after having done it thousands and thousands and thousands of times looks almost nothing like that process. And I think it's really important to note that the same steps that we apply to novice skill level people are not necessarily the ones that experts should use. And so, to come back to our pilots, these are both expert level people. They spend so much time flying planes that everything is a sort of subliminal action. They almost completely and inherently understand what they're doing without any reason to believe that they know directly what the reason they're doing it for is. And so if we expect these pilots not to make mistakes, we have to ask the question, what happened? And one way that we could do that is by looking at what happened with the plane. This is where we're going to get just a little bit technical about how aeroplanes work, but it's useful to elucidate the point. There are 2 mechanisms primarily involved in slowing down planes when they come into land: speed brakes and thrust reversers. Either of these mechanisms deploying would have effectively stopped this plane from rolling off the end of the runway. As a plane comes down to land and its wheels come into contact with the ground, it applies braking forces through those wheels in order to slow down. But there's a core problem. A plane going quickly is designed, by virtue of the fact it's a plane, to generate lift over the wings. You have to disrupt the airflow some way, and that's exactly what the speed brakes are for. They're flaps that come up on the wings, cause them not to be a lifting surface, increase the downward force on the plane, which increases the effectiveness of the brakes and the wheels. I told you the pilots failed to deploy this, but 30 minutes before they landed, they executed a standard checklist for landing at this airport, which includes turning on a mechanism which automatically deploys those speed brakes. The plane comes down to land, and the lever that indicates the speed brakes are deploying actually begins to move backwards. And so the captain, the pilot monitoring, not the pilot flying, calls that the speed brakes have deployed. And then, seconds later, that lever snaps forward, the speed brakes undeploy, and they fail to continue to automatically deploy. The automation in the machine failed, but one question you might ask is, were the pilots being too reliant on the automation in that plane? Well, This failure has never been found in another aircraft of any type that has this mechanism anywhere in the world. This is more than a 1 in a million failure, and so the pilots were unlikely to have ever seen it, and therefore I think it's not reasonable to assume that they would have known what to do. As to the thrust reversers, these are basically a mechanism which literally reverse the direction of the thrust coming out of the jet engines of the aeroplane. As your plane comes into land, they can't be turned on until all 3 wheels are in contact with the ground. And then you pull your thrust levers back, those cause the thrust reversers to activate and slow the plane down. It's very common for planes to bounce a little bit as they're landing. I'm sure many of you have experienced this. And it turns out that in this particular Boeing model, there is a 10 microsecond window in which pulling that lever back will cause a rare thing to happen, which is the thrust reversers lock out so that they can't be deployed, because usually if you try to do that while flying, you would crash the plane and that would be a disaster. And so the pilots encountered this failure, but they didn't know what was happening. They both stated in their interviews after the incident happened that they had no idea that this was a condition that could occur, and that they were continuing to pull the lever back, trying to deploy the mechanism, when that would never have worked. They were locked out. And so, if we look at this analysis, if we just look at what the machine did, we sort of begin to get better answers, but still not ones that are totally satisfactory. One solution that we could have here is build better machines, build ones that don't have these failure modes, but the truth is, both of these failures occur less than 1 in a million times, the composition of which means that it's less than 1 in 1,000 billion times. We, as software engineers, do not build systems that reliable, and so it would be sort of less than fruitful for me to suggest that we, as software engineers, should try and build systems that much better. We can't build perfectly machines, but more important than that is actively relying on really good automation can be extremely dangerous. We as engineers are taught and trained to automate away everything, but if you don't know how to do the manual steps to solve a problem, when that automation eventually breaks down, and it will, you're screwed. You don't have a way to get yourself out of that situation if you don't know how to solve it manually and quickly. And similarly, in our NTSB report, the accident investigators suggested that the pilots were too reliant on automation and did not know how to manually solve the situation that occurred. So, we've taken a little look at the humans here, and we've taken a little look at the machines here, but we still don't have a satisfactory answer. To get to a satisfactory answer, we instead need to look to something called systems analysis. In systems analysis, you don't just look at individual things that were involved in what failed, but at the whole system. You look at the HR, the training, the procedures, the policies, processes, machines, basically anything close or far away that may have had an effect on what happened. And what it's telling here is that what the NTSB saw as the recommendations that they made to both Boeing and the American Airlines and the Federal Aviation Authority about how to fix this problem. The first one that they suggested was pretty simple. Add an alert in the cabin that indicates the speed brakes have failed to deploy so that pilots don't get distracted focusing on other things. Boeing outright refused to implement that recommendation. They stated that they thought that would provide too much input to the pilots during the critical phase of flight and that they wouldn't be able to recover quickly enough from that incident. We as software engineers are trained to use metrics and alerting to diagnose and solve problems in complex situations, but I tend to concur. If you have too much input, too much failure happening at one time, that can become overwhelming and you can be confused about how to solve the problem. And so the second group of recommendations that the NTSB made were entirely to do with training. How pilots should be trained to deal with these kinds of failures. And this, the aviation industry took completely and strongly to heart. They actually went a lot further than the recommendations that were made and implemented a series of systems that are called memory actions. In the new model in 2018, this incident would be referred to as a loss of braking incident. And instead of the pilots trying to do one thing or the other thing in order to fix the thing, they would have been trained and memorized a complete checklist of everything that can cause a plane to fail to decelerate and re-execute everything as the landing occurs. This has proven to be incredibly effective. In incidents where this same kind of failure would have occurred, pilots are now able to accurately and quickly brake. And this is a systems fix. This is not a human's fix. This basically says, we have not given the correct machine-human combination to fix it, and so this is how we're going to do so. In addition, pilots now use a technique called cabin resource management, or CRM. This is a method of communication that ensures that the appropriate level of intervention is communicated to the other pilot in order to be able to slow the plane down. There are 4 levels. The first is called hint and tip, which would be, sir, would it be normal for us to land on the runway? Then, tell me what's wrong. Sir, we're not going to land on the runway. Finally, tell me what to do, which is, sir, sir, I am going to deploy the brakes. And finally, is do it for me, which is actually just take over control of the airplane from the other pilot. So, this fix is really interesting to me because it actually treats the human as the person in control of the incident. It says that we need to build systems around our people that are reliable even in the presence of failure of machines. And as engineers, that's kind of what we have to deal with too. Our machines fail all the time. And when they do, being well trained on how to deal with them is extremely important to me. But that doesn't say that we should have sloppily designed systems, as we as an industry, I think, are not good at this. So let's come back to DigitalOcean, and let's ask some questions about how our database got dropped in the first place. Well, I told you that our engineer used a production credential and then the database got dropped, but here's what actually happened. That engineer was developing a new feature and needed to test it against a production environment. So they pasted the production database credentials into database.yaml, booted up their local Rails app, and did their testing. They then went away for the evening, came back the next day, and the very first thing they did is execute bundle exec rspec. rspec drops your database and rebuilds your schema as part of test initialization. And that's how you get a dropped production database. But that's not a root cause. Why was our engineer able to get those production credentials into their test file in the first place? Why was a developer laptop able to establish a direct MySQL connection to the production primary? Why is a random application credential able to drop the database in the first place? Why was the developer not trained to use their own production credential to differentiate it from the application? Why is it even possible to drop a production database in a test environment? This, by the way, is fixed in Rails 5.1. It now has environment tagging. And so, when we ask these questions, we begin to hint at a bunch of really interesting systems failures that began to occur. Stopping at an individual human or an individual system rarely gives you a root cause. But also the word root cause is, I think, inherently misleading in what it says. It says that there should be one, and that it should cleanly tell you what the direct cause of that incident is. Root causes are often a confluence of failures, a confluence of factors that are not simple or easy, but instead go far away from the incident and touch every part of the system and many different people involved. They can be training, systems, procedural, or policy failures, and many factors beyond. This is all to say, not ever once, when you have a production incident, should your failure analysis say a human did a bad thing. That won't inform you. It won't help you get better at what you're doing, and your system won't improve. And so, at the beginning, I sort of referenced this idea that we're all running production systems, and we're all responsible for keeping them alive. This is my really core motivation for this talk, is that I am now responsible for engineers in a way that I've never been so before, and I care very, very deeply about making sure that when stuff goes wrong, they know how to deal with it, but also that it goes wrong pretty much as rarely as possible. And so I'm very interested in this area and us all getting better. I think doing valid and deep root cause analyses is very important in order for us to improve and prevent our systems from failing going forward. But beyond that, I think we as an industry, generally speaking, are not good at this. Most companies sometimes do internal postmortems, but those internal postmortems vary in quality extremely widely. And perhaps more importantly than that is that if you look at what the airline industry does, if you look at the NTSB, this is an external third party whose job it is to unemotionally come in and investigate and come to conclusions about what's going on. Imagine if we, as an industry, had a board like that who came in and helped us analyze what happened when our software fails. I think that would be really interesting. I think it would be really interesting if we had a list of best practices somewhere that says, have highly available MySQL, don't let random developers connect to it, and so on and so on. Like, there are things that are fundamentally true as best practices in doing distributed systems that everyone basically learns from scratch as they start to operate software. And I think it would be super cool if we had that better documented, better trained, and an industry-wide understanding of what it meant to be able to operate that software in production accurately. So that's basically all I've got. The closing thought that I'll leave you with is that it's really hard to do really good computing in production these days. Like, there are platform as a service, infrastructure as a service solutions that help, but everyone still has incidents. Everyone still goes down. Even Google still goes down, even though they don't like to admit it. And so I think we're at a really exciting time where we can improve, but I also think we as the Ruby community are not great at this. We are not great at exceptions and monitoring and timeouts and circuit breakers and all of that stuff. And so this is kind of my rallying call for all of you to think a little bit more, maybe, about your operations in production. That's all that I've got. Thank you very much. We have like 10 minutes. I will happily take questions if there are any, but if not,
We have a microphone in the middle, and also you could use this if you have questions. So Sam doesn't want RSpec questions, so
I
just ask them.
I can take an RSpec question, I don't mind.
I just said they should ask you RSpec.
Oh boy, the other keynote speaker, ladies and gentlemen.
All right, good morning. So Sam, you mentioned about fixing the process versus fixing the person. So just curious question, when DigitalOcean actually went down, when you actually destroyed the production database, what steps were actually taken by the company to actually resolve the situation and the person, not resolve the person?
That's a great question. Unfortunately, I have to give you a really unsatisfactory answer, which is that I can't tell you. The only thing I can tell you is that some of the questions that I asked are hints as to solutions we made, but yeah, like, to the point about this not really being super public, like, we did a public postmortem, you can look it up. It doesn't talk about follow-on actions in all that much detail, and I would love to be able to tell you what we did in incredible detail, but I can't.
All right, sorry, that was unintentional.
No, it's fine. The NDAs are hilarious. All right. Oh, got one. If anyone else has a question, I suggest like start walking to the mic on the floor now.
I was thinking, I'm not sure about using the examples of an engineer and pilots.
Sure.
There is difference between their roles. If engineers fail, in the worst case scenario, they won't.
Sure.
They could get killed.
You're asking about the sort of safety criticality, like, yeah, cool. I actually got this question. I've had this question before. So here's my take on this. Our systems, for the most part, are not as safety critical as airplanes. I think we all agree that most people in this room don't write software that have applications that are that safety critical, but they are as complex, right? Like, modern distributed software systems are as complex or more complex than any particular engineering system you care to look at. And so, really, if to us the most important thing is like having good, safe, enjoyable nights and weekends without our software interrupting us, I think it's very reasonable to treat them with the same level of introspection when they fail. Now, it's worth noting that we don't have to be as serious about it, and in fact, like, this is something that we're allowed to pick trade-offs on, right? Like, the airline industry absolutely cannot pick a trade-off. It's not acceptable for a human to die on an airplane. We can be like, if the website goes down every so often, it's like, fine, right? That's a trade-off we can accept. The question I'm posing here is, what does it look like to do this analysis in the maximum on one side of the trade-off, just so we can begin to understand what that one end of the spectrum looks like, right? If no one ever says that idea, then you're not really able to understand what the spectrum looks like. And like, we see this, for example, in how we do software development processes as well, right? So agile versus waterfall, like, but if you look at how Pivotal does agile, that looks like completely different to how a random startup does agile. And so it's all trade-offs, and I'm just positing the question, what does it look like for us to pick the maximum of 1 degree of the trade-offs? Does that answer the question? Great. There was one more? All right, thanks folks.